All right, finishing up, this will be the last lecture for Exam 1 material, and this is on Chapter 3. So Chapter 1, we just kind of introduced statistics and a lot of the terminology and how we label certain variables and how we measure certain types of variables and focus really on the quantitative versus qualitative. And Chapter 2, we looked at how we can display information we have in our data set graphically. And Chapter 3, we are going to do some graphs, but we're mainly going to focus on numerical descriptions of our data, and this is where we're going to get into some calculations and formulas. As far as the learning objectives that we're going to go over for this chapter, the main things that I really want to focus on is that we know the differences between measures of central location, measures of dispersion, and measures of association. So we'll be talking about different types of calculations and where they belong. So it's really important that you know, I'll go ahead and ruin it, spill the beans here, that if you calculate the mean or the average of a data set, that's a measure of central location. If you calculate, say, the standard deviation, that's a measure of dispersion. And then we'll just really introduce association. We won't spend a lot of time on it, but something like the correlation factor would be a measure of association. So really not only just knowing formulas, but knowing what category they belong to. We have a graph. We're going to look at a box plot in this chapter, so add that to your toolkit for graphing data. We will talk about the geometric mean. However, we're not going to spend a lot of time on that. That is more the calculations for that you'll do in a lot of finance. However, we do need to know that the geometric mean is a measure of central location. So I'll talk about that again. Same with learning objective 3.5. We'll talk about these things, but again, we're not going to spend a lot of time calculating them. Just know that they're a measure of dispersion. What we will focus on as far as the theory in this chapter would be Chebyshev's theorem and the empirical rule. Those are very important. And then I'll introduce z-scores, which we won't really use very much this chapter. It'll come up again in Stats 261, but it is a good idea to get familiar with them now. Okay, so let's look at the introductory case here. We're talking about investment decisions, so a lot of finance topics statistics really helps with. So let's assume Dorothy works as a financial advisor at a large investment firm. She meets with an inexperienced investor, aka me, who has some questions regarding two approaches to mutual fund investing. I wouldn't even know to ask that question. The investor shows Dorothy the annual return data for Fidelity's Growth Index Mutual Fund. We'll call it Growth, and Fidelity's Value Index Mutual Fund that we're going to call Value. And this table here is just representative of the data set. Not all values are shown here that are in the data set, but we kind of get an idea of what's included. So we definitely know the year. We know the growth value for that year and the value for this year. So a negative value indicates a loss or a decrease in the rate of return, and the positive value is an increase. So based on this value, we could do something for Dorothy could do something like this for her client. She could find the typical rate of return and compare them between the two mutual funds. She could calculate and interpret an investment risk for the two mutual funds, and she could determine which fund provides the greater relative return relative to risk. And also, you know, there's other factors that you may consider when investing. So let's get into the types of measures that we can use for central location. Central location, I've even seen it called measures of tendency, central tendency, and this is how numerical data tend to cluster around a center value or a middle spot. Measures of central location, they're looking for a typical central value that describes all the data. And the arithmetic mean is the primary measure of central location. So just like you would think of the mean, also sometimes called the average, when you add up all of your observations and divide by how many observations you had, that's how you calculate the mean. So if you have 4 test scores, you add up all 4 of your scores and divide by 4, and that would be roughly the average score you made on your exams. Now the formula for for the mean, a measure of central location, depends on if you're looking at the population values or the sample values. And remember, the population is the larger group, and the sample comes from the population, but it's a smaller group. It's a representative of the population. And so if you are able to calculate mu, which is our population mean, you would actually be calculating mu by adding up all the values that are here and dividing by how many you had, capital N. So Greek letters represent population values, and in this case we use capital N to represent the total population size. Now, typically we don't have enough time, money, resources to calculate a population mean, so we take a smaller sample out of our population and we can calculate values there. Now, if we want to calculate a mean of the sample, then we're calculating X bar. Okay, so they're both means. One comes from the population, one comes from the sample. Okay, this is important. So they're both means, but it depends on where they came from, how they get their label. Okay, and if you want to calculate X bar, you add up all the values in your sample and divide by little n, and little n represents sample size. So capital N is population size, little n is sample size. Another thing you may not be familiar with is this Greek notation sigma. You can see already, like, they don't put all the data in the data sets when we look at PowerPoint slides. Typically, as mathematicians, we have labels and shorthand for almost everything. This sigma stands for the property sum. Since the summing up starts with an S, the Greek letter sigma represents S, and it just means add up all of your X's, and the X's are each of these observations that you have in your population or your sample, depending on what you're looking at. Add up all of your X values, where you start with the ith value, but I could be 1, 2, 3, 4, all the way up to however many you have. Okay, so it's really a shorthand notation that says this right here means to sum up. So sum up all of your observations from X1 to X, however many you have, and then divide by how many you have. And so it's just a shorthand notation. Now, the mean is the most common. It is typically the one that is presented when you're looking for a central location, a measure of central location. However, it can be a little bit misleading if you have values that are really, really small or really, really big in your data set, because the mean includes the weight of all those observations. So it can sort of think of the mean as like a balancing act. So if there are if there are more observations on the extreme upper end, it might tilt the mean to be a little bit higher than really is what representative of the actual sample. Okay, so if we're using the data set, the growth and the value data set, that we started with in our introductory example, we could calculate the mean for the growth fund and the mean for the value fund by adding up all the individual observations. Now this just means there's more values that we're not showing that were into our calculation, and then divide by how many we had. So we had 36, over 36 years basically, we were able to find the rate of return for each of those years, add all those up and divide by 36, and on average we have a positive growth factor of 15.775, an average mean return for growth and value. If we do the same thing for the value, we add up all the values over the 36 years and divide it by 36, we get 12, and it's positive, so that means an increase. So the good news is, I think, no matter whether you go with the growth fund or the value fund, you're going to make money. So that's good. And we can see here quickly by looking at our data, and that's really what we're doing, whether we're trying to put our data in a graph or we're trying to perform formulas and calculations, we're trying to be able to take a look at a large amount of data, typically, 36 is somewhat large, and be able to pinpoint some key things about this data that can help us in our decision making. When you just look at raw data, all 36 observations, you really have no idea which one's better. But if we can start graphing, we can start summarizing with formulas, then we can get a better idea and we can make claims like this. We think that the mean return for the growth is greater than the mean return for the value fund. And that's a true statement, right? And without summarizing the data, we may not be able to see that that's what's going on. However, they allude to, we'll see, we would be ill-advised to invest in a mutual fund solely on the basis of its average return. Okay, so there's always other things to consider, but this is a good starting point. All right, let's look at this example right here. These are salaries of employees at a company called Ace Tech. And we have 1, 2, 3, 4, 5, 6, 7, 8 employees. And we have the title of what their job duty is, and then the average, their salary for that job duty. Okay, so these are all the employees. So that means we are working with the population. So if we're going to calculate mean here, we're calculating mu. So how could we calculate mu here? Well, we would add up all of our values, 40 plus 40 plus 65 plus 90 plus 100 plus 145 plus 150 plus 550. And when we calculate all those, add all those up and divide by 8, we'll get our average number, our average salary. Let's see if they do that for us. They don't do that for us, so I will do it for us on my calculator. I'll pause. Okay, so when I add all these up and divide by 8, I get an average salary of $147,500. And so you can see here with a mean of 147,500 that there's this is a little bit maybe skewed. So we see here that we have most everybody in the data set earn less than the mean. So that's maybe not very representative of the average salary. As far as, if I were to recruit you and say, I would like you to come in as a research assistant and we pay our employees on average $147,000, you're going to be like, oh my gosh, sign me up, right? And that's a little bit deceiving. So you need to be very careful when you do see a mean, especially when it's on salary and home prices, really anything to do with money and the amount that's either sold or paid. The mean is maybe not always the best value to find the center. I always ruin this example, but I want to say, the University of North Carolina, on average, if you look at all of their data over however long they've been an institution, they have the highest average starting salaries for their business students. So maybe we should all just drop out and go to University of North Carolina and all enroll as business students and make our high salaries, right? Well, that's deceiving, because do you also know who went to University of North Carolina in the business program? It was Michael Jordan. Okay, so his salary really skewed the data. And so you really, in general, would not want to include his salary unless you're trying to recruit people and you want to be a little bit deceitful. But that's the problem I think people have with statistics, is that it can seem deceitful. This is a correct number. We did the calculations correctly. But you also have to be very, very, aware on either end that if you're presenting these values or you're reading about these values, that you know what the max and the min are, so you can see where the discrepancies are, if any exist. Okay, so since the mean can be affected by, we call those extreme values to the right or to the left outliers, the median is the approach that we use instead of the mean. So the median, I told you to think of the mean like a balancing act, like with weights. Well, the median is just the physical middle. It doesn't really care if it's balanced or not with the values. It cares if it's the balance because it's the physical middle of an ordered data set. So the median is the value that divides the data in half. You have half the data above it, half the data below it. If you have an odd numbered of data set, odd number in your data set, then the middle value will exist. If you have an even numbered data set, you have to take the average of the two middle values. And I want to make sure it doesn't do a good job right here. The median is the middle value when you have ordered. Okay, so not always do we get data that's in ascending or descending order. If your data set is like all over the place, 6, 17, 10, 4, 5, and 12, you have to put it in order first. Okay, so that's a mistake that I get seen that's made quite often, and it doesn't really do a good job here of emphasizing that. To find the middle value to use as the median, it has to be in order least to greatest. So the median is what we use if we know there's outliers present Most of the time, if we use the median, we'll also show the mean. And if they differ a good bit, then we kind of, it's understood why we use the median over the mean. Okay, so let's look at an example. And let's see if we can find the median salary of Ace Tech employees. So here they do finally make a note here. First thing you have to do is you must put them in ascending order or descending. It really doesn't matter. So we've got, and they were listed originally that way. We have an even numbered data set. That means we're going to go to the two middle positions, take those two salary values, add them up, and divide by 2. Okay, so we see here that if we go to these two, we have 3 values above it, 3 values below it. We'll take that average value. 90 plus 100 is 190. Divided by 2 is 95,000. So we can see here that the median salary is 95,000. That's a little bit closer, a little bit more representative than the mean, but we still have quite a few actual values that are below the median, but we have just as many above. So it seems to be pretty fair and balanced. Again, you would probably still feel deceived if you came in, as a research assistant, if it wasn't made clear that it depends on the type of work you're going to be doing. Another common measure of central location is mode. So often you'll hear those 3 recited together, mean, median, mode. The mode is the value in your data set that occurs the most frequently. You can have one mode in a data set. You could have multiple modes, 2 modes. You can also have the case where you have no mode, where no value is duplicated. And the mode is it's really not as useful as the median or the mean and rarely gets reported. It is useful as far as statistically when we're looking at how data is distributed or how it's shaped. But as far as being reported, I don't think it's really reported very often. The mode salary for the employees at the Ace Tech, if you remember, let me see if I can go back. You see that we have 40,000 listed twice and no other value repeats. So 40,000 would be the mode here and the only mode. But again, on the other hand, if I only reported the mode to you and said, well, the most frequent salary at my firm, I would love for you to come work for me. The most frequent salary that we pay people is 40,000. Well, that may not be equivalent to what you're doing right now, but you may not have the full story. Okay, so in cases like this, especially with salary and home prices, it's probably important to report all 3. Here's another example using categorical variable where you can find the mode. And this would be an example of women's sweatshirts. So they come in size large, small, medium, and large. And you can see here, we've got small twice, we have large 5 times, and we have medium 3 times. So, oh my gosh, what do I do? Well, even though small repeats twice, that's not the mode, because it's not the most frequently repeated observation. And the same with medium. Even though medium is repeated 3 times, it's still not the most repeated value in the data set. The mode of the sweatshirts here would be large because it is repeated 5 times, and that basically outranks the other frequency of repeated. The only thing that could happen here is, let's say we added extra large and it repeated 5 times as well, then that's when we have 2 modes. Okay, so it has to be the most frequently repeated value above any other repeated frequency, and only can it be bimodal if they have the same value of frequency. So I hope I explained that correctly. Okay, here are some measures of central location. And how you can calculate them in Excel. So far we've talked about mean, median, and mode. And these are the Excel functions that you can use on a data set. And this right here, we're not going to get into this yet, but I'll do a quick plug for my new class called Introduction to Data Analytics. R is a programming language. It is free, and I'm going to teach students in the ST345 all of these things in R. So basically, we're going to relearn a lot of what we did in this class and how to use programming language to get the same results. Why? Well, believe it or not, in industry, not only do our employers want 1, professionalism, 2, Excel skills, and 3, familiarity with other data analysis software. And so with this new class, I really think it's going to be a great skill to add to your tool set, no matter what field you go into, that you have not only, even if you never program in R outside of that class, at least you've been exposed to R. And you don't show up day one on the job and have no idea what R is. So I'm really excited about that class. Hope to see you guys in it. I'm going to offer it this summer. You do have to complete Stats 261 first before you can be in it, and I will be offering it in the fall. So hopefully you get another opportunity to hang out with me. Anyway, back to the real lecture here. We've gone over mean, median, and mode. Maximum and minimum are also measures of location, and I should go ahead, but I'm not sure. Minimum is the smallest value, maximum is the largest value, and then we'll talk about percentiles soon. Okay, so if we were to put our data in Excel, back to the introductory example, and calculate measures of central tendency for growth and value, I can show you how to do this in Excel, and I will in a different video. You can see we get all these values out of Excel. So we can see that on average, the growth fund is a little bit higher return than the value fund. But if we compare the medians, they're a little bit closer. Interesting. And both data sets do not have a mode. So now what? Now what would you choose to tell your client? What would be best? Or as a client, what would you choose? Right, if you have all the data. Well, you see all this down here? There's more to the story. Let's learn. Sometimes it's useful with measures of central location that when we see discrepancies like we have here, where the mean looks a lot different but the median isn't, we may need to subset our data. Maybe there's another variable that's impacting what's going on. So in this case, this is a totally different example, but we have a data set where we have customers, we have their gender, their clothing, their health, their tech, and their miscellaneous spending. Okay? And so when it's all listed together, when you have female, male, there's really no way to know just looking at the data, how the spending is distributed. Now, we can still calculate overall averages on all of our variables, and that's important to do too, but we may see something revealed if we're able to separate into males and female spending. And as you can see, stereotypical as it is, right, in this data set, it looks like women will spend more money on clothing than men, and that men spend a good bit more money on tech purchases than females. So very interesting. And then miscellaneous, I guess that, I don't know. Is makeup considered health? I'm not sure. I would say probably, that might be more of the miscellaneous, and I'm trying to think what else I spend my money on. Mainly groceries, not exciting stuff. But anyway, that insight would not have been available to us if we were just looking at the data overall. But once we subset it on a categorical variable, we get some really interesting things show up. Another measure of central location is the weighted mean. And this is when we have a reason to believe that some observations carry more weight than others, and so we want to apply that weight to make sure we get the correct estimate of the center. So as far as a formula goes, we give each of our weights represented by W1, W2 up to Wn, and then we have each of our observations x1, x2, xn. And so the only rule is that if you add up all your weights, you should get a percentage of 100%. So when you're thinking of the weighted mean here, or the weighted mean here, I like to think of it as grades. So let's say you've been in classes where your homework is 15%, right? You've got quizzes and they're 15%. You've got exams and they're 50%. I'm just making this up. I don't do weighted means. So that's 80, and then your final is 20%. something like that, where the different assignments are weighted differently. That's a good example of a weighted mean. And if I add up all my weights, I should get 100%. So the weighted mean, really what you need to know, I'm not going to ask you to calculate it on your test, but you need to know that the weighted mean is a measure of central location, and it can be found with this formula. So instead of summing up just your x values, you multiply each x times its weight and then sum it all up. So for example, here we go. Let's look at a student score. Exam 1 was a 60, exam 2 was a 70, exam 3 got an 80. What's the student's average score for the course if exam 1, 2, and 3 are weighted 25%, 25%, and 50%? Okay, so weight 1 is 0.25, weight 2 is 0.25, and weight 3 is 0.5, corresponding with these percentages. And the formula says to find the weighted mean, and sometimes people will denote it X bar W, so it's different than the unweighted mean. You would take each weight and multiply by each observation. Well, each observation means the score on the test. Okay, so the first weight times the first score, plus the second weight times the second score, plus the third weight times the third score. So when you multiply those first and then add them all up, you get a weighted mean of 75.5. Now, if you just add up 60 plus 70 plus 80, 150 plus 60, you get 210. If you divide 210 by 3, you get 70. So that's the unweighted mean is 70. So this person did better when it counted. Okay, we talked a little bit about symmetry in chapter 2, and so here's just more of a discussion on some if a distribution is symmetric. So remember the histogram. If a distribution is symmetric, then it is a mirror image. You can cut it in half, flip it over, and it will be the exact same shape on either side. Symmetric distributions are unimodal, meaning they have one mode, and a symmetric distribution guarantees that your mean, median, and mode are the same value. So that's interesting. If you have a positively skewed, remember positively skewed means that it's skewed right, which means the tail area is in the right. So that'd be positively skewed. Whereas negatively skewed, the tail area is in the left, and we have a negative. Okay. So if you have a positively skewed distribution, then the mean is greater than the median. And if you have a negatively skewed distribution, that means the mean is less than the median. And remember, that's because the median is the physical center of the data set. And the median is the physical center, and the mean is where the balancing act is given. So we want to make sure we have the same amount of weight in each thing. Okay. So we have a skewness coefficient that we can calculate, but really all you need to know is just that you can have no skewness, which means it's symmetric, and you can be positively skewed or negatively skewed. Okay. A percentile, I'm sure you've heard of percentiles before. If you've ever taken like a standardized test and you get your results back and it says you're in the 96th percentile for this topic, and that just means that basically 96%, you scored as good as 96% of your peers, only 4% scored higher than what you scored. So percentiles are what we use when we need to create a box plot. So a percentile is a measure of location, and it's also used to measure the relative position because it's easy to interpret. So make sure you know percentile, measure of location. The percentiles that we are most interested in typically in statistics would be the 25th percentile, 50th, and the 75th percentile. Now, they get their special name. So remember I told you we like to give this the same thing a bunch of different names. When you're able to divide your data up into 4 groups as we are here, these are actually called quartiles instead of percentiles, or it's interchangeable really. The 25th percentile is the first quartile. And so that's why it's called Q1. Typically, we're going to let software do these calculations for us because it can be kind of difficult. You know, the idea about the median and the center, we have run into the same issue when we're trying to find the cutoff value for the data points within the first 25%. So we typically let software do this for us. And the main thing that we end up looking for is we're trying to get a 5-number summary. And with this 5-number summary, it's very easy for us, which we don't do this by hand anymore either, to draw box plots. And the 5-number summary is where we have the mean, the standard deviation, the minimum, the quartiles, and the maximum. Or maybe I've got it wrong. I guess these quartiles are considered 3. So 5-number summary, that's hard to say. 5-number summary is where we look at the lowest value, the biggest value, and then how it's broken down in between. Something that's very interesting as far as box plot is the IQR. And the IQR, so range would be, you know, the max minus the min of a data set. The IQR is where we look at what's happening in the middle of the quartiles. So I'm just going to ruin the story here. All right, so a box plot looks like this. This would be Q1, Q2. If we're, you know, this is the ideal symmetric. So, and then this would be the max up here and the min. Right, so we're always interested in the max and the min and how that difference looks. And that gets its own name as well. We'll talk about that in a minute. Or maybe not. Remind me. Oh, I did. I told you the range. So the range is called the max minus the min. Another thing that we're interested in is how much area is between Q1 and Q3, because that's where the bulk of the data is. And that thing is called the IQR, or in words, the interquartile range. I don't know why they don't spell that out. Okay, so back to our mutual funds. Which one should we invest in? Let's not worry about R. With Excel, we're able to find the minimum, Q1, Q2, Q3, and the max for both growth and value. Okay, so now let's look. The minimum value would be basically the worst loss, right? So we can see here that value lost more at one point in time than the growth did, but they both lost in the 40, so that's kind of scary. The 25th percentile value was 2.86, and for growth and for value it was 1.7. And then the median, so the Q2 is another name for the median, remember, was very close. Q3 would be the cutoff for the 75th percentile, so that means 25% of the data is above it, 75% is below. And you can see here that this is where the growth fund is starting to outpace the value fund. And we can see here the max is almost double, right? So the growth fund can achieve much higher return than the value fund. Okay, so here's what I was trying to talk about before, the box plot, and it's how we, using the 5-number summary, we're able to really plot our values for the box plot. But again, we typically use software to do this for us. But this is a box plot. Sometimes it's called a box and whisker plot. So you definitely have the box. And this little line down the middle is the median. It doesn't have to be in the middle. This is just where the median is. And where the box starts is the Q1 value. And where the box ends is the Q3 value. And then you have a line, and this would be your max value here, and then your minimum here. And since we have these lines, they kind of look like whiskers on a cat. That's why it's called the box and whisker plot. And then in most cases, software will report any outliers. So values that are significantly further above the max than expected. And that, well, I guess that's why they didn't label it the max, is because we have the outlier here. You could also have outliers on the other end as well. And then if we were, this right here would be the IQR. Again, we let software do this for us, so there's really not a need to go into detail how to do it, but the box plot is another important graph that we use when we have quantitative data. And why we do that is because we're obsessed about the distribution, the shape of the distribution, and we can also figure out symmetry or skewness based on the box plot. Okay, the geometric mean, like I talked about before, we're not going to focus on this. You just need to know that the geometric mean is a measure of central location. Okay, so hello, Finance 301. You'll have fun with that. All right, I think I'm going to pause here and then we'll pick back up with measures of dispersion in another lecture because I've already chatted for over 30 minutes.